Okay, this is unit 4 of the Arduino series of units that are part of CSC270 at Smith College. So in this unit, by the way, you'll be interested to look in there and see if you recognize anything. This is taken from XKCD. Always interesting and fun cartoons on computer science. So I want to treat about communication, units 4 and units 5 of this series. And first, we're going to look at parallel communication. And at the end of that, we'll look at some terminology. So I'm going to switch to the iPad so that I can annotate my slides. So in parallel communication, the parallel comes from the fact that the data is sent, all the bits are sent at the same time, all the data bits. So the easiest and simplest of communication is parallel communication where one byte of data is sent from a sender to a receiver. So here we assume that data is going to flow this way. Going to go from the sender to the receiver, and here is the data. So I have 8 bits. That's a byte here, and that's typically an ASCII character. Can be data, of course, can be an integer or part of a float, but typically 1 byte. So think that a character is being sent over 8 bits. So these are wires here that you see between 2 devices. So I'm going to assume in the rest of the unit that these are Arduinos. So one Arduino is sending to another Arduino. And so the way to do that is to use 8 digital pins on one Arduino and have 8 wires going from these 8 digital pins to the other Arduino to 8 digital pins. And so on one side, the digital pins will be outputs. And we know how to do that from previous unit. Pin mode, particular pin number, output. And then on the other side, these wires will be connected to digital pins. They can be exactly the same number, the same pin numbers, but these will be programmed as input. And of course, what we need to do to make sure whenever we connect two different systems, electronic systems together, we ground both. We have a wire or several wires connecting the grounds together. So here, in order for the receiver to understand when something is coming, it would be, logically, we think that when bits are being sent from one place to another, they just go and then the lines remain idle afterwards, and the receiver can figure out when the byte is coming over. But assume that the sender is sending the same character many, many times. Maybe it's a space, and there's a lot of space somehow between characters, or so the ASCII character for space would be sent 10, 20 times maybe at a time. So how would the receiver be able to determine where the beginning of a space character is and where the end is? So in order to somehow truncate that or indicate the beginning of a character being sent and the end of a character being sent, the protocol, and that's a standard protocol for exchanging information, the protocol will use 2 extra lines. So one will be called strobe, so that's what the STB here is for. It means strobe. That's the name of a signal that is sent by the sender to the receiver. So the receiver has a pin, a digital pin used as input that is going to receive the strobe, and is going to listen to that signal to see what the sender is telling it. And the receiver will respond back to the sender by activating a signal called ACK for acknowledge. And so the ACK information is going from the receiver to the sender, and they communicate with each other using a protocol that we're going to now look at. So this is how this is going to take place. The first thing that the sender is going to do is going to send the data bit. So I'm going to show this as signals going high and signals going low, because when the sender sends a new byte, some bits are going to change. The byte that is being sent is not necessarily the same as the previous one, So this is the first step. The first step, 0, the sender puts a new data byte on D0 through D7. And then as soon as it's done that, it's going to activate the strobe. So a little bit after, that's step 1. The sender activates strobe. And the receiver is going to be listening to that. It's going to be looking at the value of that signal. And as soon as the listener sees that strobe is down, it understands that there's a new byte available on its D0 through D7 inputs. So if we go back here, the receiver right here is listening to strobe. It's finding out that strobe has been activated. So what it can do, it can take this byte and store it somewhere in a buffer, print it, do whatever is needed to be done. All right. So it will do so. And as soon as it does so, it's going to activate the ACK signal. So ACK, that's step 2. It's the receiver telling the sender, okay, I got your byte. I've processed it. So as soon as the sender sees that, then it puts its strobe signal back up. So that's 3. And after a little while, when the receiver has looked at strobe and seen that strobe has gone back up, it brings acknowledge back up. And what is important, so let's change the colors, is that if you look at this instant in time, there's an interlocking. There's 1 that happens first, and then 2, and then 3, and then 4, which I forgot to label right here. So step 0, so we're going to summarize here. Step 0, the sender puts a new byte on the wires, going through the cable to the receiver, and then activates strobe. That's step 1. And you can think of step 1 as the sender saying, hey, receiver, I have a new byte for you. And then at some point, the receiver will notice that the strobe signal has gone down, low, and it will grab the byte from D0 through D7 and do whatever it needs to do with that. Whatever the receiver is supposed to do. Probably put it in a buffer somewhere in an array. And then when it's done, step 2, the receiver will say, oh, I got it. So that's step 2. And step 3, the sender will change its strobe saying, oh, I see that you've gotten it. So now I'm good. I'm done with what I was supposed to do. I sent you the byte. And then step 4, the receiver is saying, oh, I see that you are now fine, and I'm ready for a new byte if you want to send me one. And so you see that at step 5 here, so I'm going to write this as 5. 5 is exactly where we were when we started. And a new byte can be sent by the sender to the receiver. So we call this a handshake protocol. So that's what this is for. So let's use a bright color here. This is a handshake. And because this controls how information protocol, how information is supposed to take place, information exchange between two devices, that's a protocol. And if both sender and receiver follow and obey the protocol, the good thing about this interlocking of strobe and ACK is that the one will never go faster than the other. And the sender can be extremely fast and the receiver extremely slow. They will still exchange 1 byte at a time. There's no overrun possible. And similarly, if the sender is very slow and the receiver very fast at absorbing the data, they will not be able to lose information. All right. So the rule that I want to emphasize here is that whenever you connect 2 devices together, so you have device 1, so that's the sender, and it's sending information, so you have many wires. So that's typically a way of representing a collection of wire. We just saw 1 arrow, we put a slash through it, and we write the number of bits. I have n bits sent from device 1 to device 2. Device 2 is the receiver. So what you want to make sure is that the ground on one side is connected to the ground on the other side, and we'll show that as being a ground pin. And that is important. Why is it important? Is because if you imagine that, I'm going to draw another line, just one signal, and imagine that there's a current that is going here. So maybe there's a high voltage being sent by the sender. So a high voltage means that current is going to flow from device 1 to device 2. So this current has to come back and to the source, and the source in this case is device 1. So for the current to come back, then the ground wire is a perfect place for it to do so. And you can see that in some cases, even when data is sent over several wires, in some cases we're going to have a ground wire associated with each data line. So just having one is fine. So in a diagram that I have here, I'm showing one ground wire right here. That's the ground wire. But in some cases, you may have many. And actually, if you have n data lines between the sender and receiver, you could even have n wires just for ground. And so that if you look at an Ethernet cable, you're going to find that this is actually the case. So if you look here at the white wire that is here, and the white wire that is here, and the white wire that is here, and the white and blue wire that is here, these are ground wires. These are wires that are going to be used for ground connection. Ground, ground, ground. And a benefit of doing this is that we're going to twist, so these are called twisted pairs, cables containing twisted pairs. These ground wires going around an electrical wire are going to create some kind of shield, because rule of electromagnetics is that if you have a wire and a current that is oscillating fairly fast, and these bits go very, very fast at megahertz typical rate, then the wire acts as an antenna, and it's going to create magnetic noise all around us. So having these twisted ground wires around kind of limit the amount of antenna power that we create. So a typical example of that handshake protocol we find in an old communication protocol called the sentronics interface. And that's how old printers in the old days were connected to laptops. It was a cable with a lot of pins, because we were connecting we were sending all these bytes, 1 bit in parallel, 8 bits in parallel, plus the strobe, plus the acknowledge, and ground, and other wires as well. So it was a little bulky. It was bulky on the back of a terminal. So this is a laptop from maybe 15 years ago. And you see that it has this Centronics interface with 25 pins in that connector. It's called a 25-pin connector. So it was bulky. The good thing, though, if you have different speed, the advantage of the handshake protocol is that you don't lose ever any bytes. So wiring, it's bulky. Connectors, bulky. So now we don't have parallel cables associated with laptops. We have serial ports. And USB has kind of displaced parallel communication from laptops. All right, so how would that look like if we had two Arduinos communicating with each other? Well, I have sketched that by having this a program for a sender on the left side and a program for a receiver on the right side, but I've only shown the comments. I'm not interested first in looking at the code, just want to look at the logic. How would we go about this? So the first thing I would do is, in the setup, I would set up all the pins on one side, the data pins as being output pins. So that's what I'm representing here. D0 through D7 would be output pins. Strobe would be an output pin, so it would go out towards the sender, to the receiver, and the ACK would be an input, would come from that. So this would correspond to that, going here, and ACK there. So you see that on the receiver side, strobe would be an input, ACK would be an output, and the data bits would be inputs. So the data would go from sender to receiver that way. All right, so setup in both sender and receiver, what we would do is we would set the direction of the data flow. And then the sender would set its strobe high, which is the idle mode, and the receiver would set its acknowledge high. So that's what we see here. And that you do once, and then as soon as the sender wants to send a byte, that's what the loop is going to do. The loop, every time the loop runs, we're going to assume here that it has a byte to send. And so the byte that I've decided to use is uppercase A, that's the character A. And in ASCII, A is 0x41, which is 0100 0001. So these are the 8 bits that would be sent over D0 through D7. First step, what needs to happen at the sender side? Digital write all the bits on D0 to D7. So that's the first step. And followed by setting the strobe to 0. So that's the first part of the handshake. And then the sender is going to wait. It's going to wait to see if the acknowledge of the receiver is being activated to tell us that the receiver has absorbed the byte that was sent. Once that is discovered, we move on to step 4, and we set the strobe back to 1. And then we're going to wait until we see that the receiver has returned its acknowledge to 1. So that's the last part of the handshake. So similarly here, when we're on the receiving end, the first thing that we have to do is we have to wait. So that's this part. The receiver will not know that it has received the byte until it sees the strobe actually going low. So that's what it's doing here. Wait, loop for strobe to become 0. Step 2, as soon as we have seen that strobe has gone to 0, the receiver will grab all the bits, 8 of them, from D0 through D7 using digital read calls. And after that, once it has read it, it will put it aside. So I don't have this here, but it will put it in a buffer or in an array. And then it will acknowledge, it will set ACK to 0 to tell the sender, oh, okay, I got it. So that's step 3 on that side. And then step 4, the receiver is going to wait to see the sender activate its strobe. And then it will set its ACK to 1, and now it's ready to receive a new piece of information. So that's exactly what we were doing here. So that's fairly simple to implement a handshake protocol and to exchange a byte from one Arduino to the next. All right, so now comes a computer science question. How fast could our @mega send a byte to another @mega without any more information than what we've covered so far in these units? So think about that. What would we need to put together in order to figure this out? How fast? And we don't know too much, but we know several things. We know that the clock speed of on the @mega is 16 megahertz. We know that the @mega processor is a RISC processor, which means 1 instruction per cycle. So 16 megahertz will translate into 16 million instructions per second. And so, all right, how many instructions will it take for a sender to send a byte at the fastest? Because that's what I'm interested in. What is the fastest transmission speed? So we need to get an order of magnitude. We know we're not going to be able to measure exactly or to get the exact count, but I want to be getting within an order of 10. And so one way to do that is to look at this code that we have right here and look at the loop and see how many instructions is that taking. Well, I don't know the assembly language of the @mega processor, but I know in instruction set of the Pentium 32-bit instruction set. So that's what I'm going to be using because I know that instructions are similar. They're not the same, but they're similar. They are going to be move instructions, they're going to be add instructions, they're going to be jump instruction and test and so on. So that's what I'm going to do here. So I'm going to say step 0 is to set a byte to A. Step 1 here is digital write all the bytes to the output pins. Step 2, set strobe to 0. Step 3, set the ACK to become 0. Step 4, step 5, and that's it. So I have to translate this into a number of instructions. Vaguely. I don't need to be very precise. I just want to have an idea of how long each thing is going to take. So here, step 0, a byte is equal to A. So I could imagine doing something like this. I could imagine putting into AL the character A. And I'm going to put here on the side 1. It takes 1 cycle to do that. And then digital write all the bits of the byte to D0. So step 1, how can I do that? Well, in a Pentium, we don't cover that typically in the assembly class at Smith, but there's an in and out instruction for outputting a byte to some port or inputting a byte from a port into a register. And usually AL is a register that is being used. So here I could imagine that I could out to some, say, D0 AL, and that would be enough to send the least significant bit of AL into some port and be out. So I'm going to assume it's going to take 1 instruction. And then I need to shift right AL by 1 bit, so shift it down, get rid of the least significant bit and shift all the bits down. And then I can out AL onto D1, a different pin, and then shift right AL by 1. And if I do this a total of 7 times, then I'm going to output all the bits. So that means that I have a out and shift roughly 8 times. So that would be 16 cycles. Again, I'm using an approximation, but it's going to help me figure things out. 2, set the strobe to some level. So it's just going to be out. I'm going to assume that I have a port that I'm going to call strobe, and I'm going to output the value 0. So that's 1 cycle. 3, I have to wait. So that's more complicated. I have to wait. So I have to read a port, check its value, the value that I'm reading, and if it's not what I want, I keep on going. So I'm going to have a label while, maybe while 1, because I'll have another loop later. While 1, in ACK AL. Get the value that I'm reading from the port that I'm labeling ACK right now, put it into AL. Compare AL to whatever I'm expecting it to be, and jump, if not equal to what I want, to while 1. All right, so that's kind of an infinite loop that is going to break as soon as what I'm reading into AL is the value that I want. So that's basically 3 cycles, 3 instructions, 3 cycles. 4, set the strobe to 1. 4, so that I've done before, so it's out, strobe 1, 1 cycle. And then 5 is I have another loop that is going to wait for the ACK to be the value that I want. And again, I'm interested in the fastest that this code could execute, so I'm going to assume that I don't have to wait. So I just go through the while loop only once, and that's enough, and the condition that I want will be met. So 5 is the same as step 3, so that's 3 cycles. So let's add that. So 1 plus 16, 17, plus 320, plus 121, plus 122, 25. Okay, 25 cycles. 25 instruction, 25 cycles. I'm going to say 25 is equivalent to 30 cycles. So I'm rounding up here, and I know 1 cycle equals 1 over 16 million seconds. All right, so sending 1 byte is going to take 160 millionth of a second. So if you do the inverse of that, I'm going to find that roughly, approximately 500,000 let's see, 500, yeah, 1,000 bytes per second can be sent that way. That's the maximum speed, half a megabyte per second. So you see how I can, using just the information that I know and rough approximation, I have an idea of what I could expect. So in a real system, maybe it's going to be 100,000 bytes per second, but I'll be in the ballpark. It will not be 1,000 bytes per second. It will be much more than that. Okay, so I'm setting the byte to A. Digital write. So here what I'm doing is that I'm kind of skipping a step, but somehow I need to transform byte into different bits, and for each bit I'm going to set whether it's high or low and put that on one of the digital pins. So I'm skipping that. I'm not showing how I'm doing this in C, but it's possible to do that. Then digital write strobe, and then here is my while loop to wait for ACK to be low. So as soon as ACK that I'm reading with the digital read is low, then I'm breaking out of the loop. So while one in C is an infinite loop. And then digital write strobe high, and then another while loop to wait for ACK to be back up to high level. So that's what it would look like. So it's fairly simple. You don't have to think too hard. So that's for parallel communication. Now, a few words about terminology. Whenever you talk about communication between devices over some kind of cable, over some kind of link, you want to express it as whether the communication is synchronous or asynchronous, and whether it's simplex, half duplex, or full duplex. So synchronous or asynchronous is very simple. If the transmission passes on a clock or sends a clock signal along with the data, it's synchronous. And what that means is that bits or bytes are going to be sent and received at similar time ticks. Okay, so if you want the sender and the receiver to operate together in parallel at the same time, then you need a master clock, and usually the clock is going to be sent by the sender. That's what synchronous means. If it's not, if there's no clock signal being sent, then it's asynchronous. So the example that we have of sender and receiver, that in parallel, it's asynchronous. We don't send a clock. We have the handshake signal, but that's not a clock signal. It's something that is not synchronous. So we have an asynchronous communication. Okay, simplex, half duplex, and full duplex. If data always goes one way, like in this case, always goes from the sender to the receiver, that's simplex. If every so often data is going to go one way or the other, then that would be half duplex. And if it is possible for data to go both ways at the same time, that's full duplex. So think of it as a bridge with a traffic of cars. If the bridge is one way, so there's, cars will always go one way on that bridge, that would be a simplex kind of communication. If you only have one lane, and so cars can go in one way for a while, and then a traffic light will allow cars on the other side to go in the opposite direction, so that would be half duplex. Because you only have one lane and you can only have flow in one particular direction, so half duplex. But if you have a bridge with two lanes and cars can cross at the same time, that would be full duplex. So that's how we refer to that with data communication. So the question is, the parallel protocol we just saw is asynchronous. So let's use this instead, asynchronous, and it is simplex. Data always goes from the sender to the receiver. Receiver never sends information back in that case. So that's the communication that we've just seen. So a review, so always review the slides. That's my recommendation. Quiz has questions that are going to depend on just what I covered here. So summary, the handshake protocol is very easy to implement with just two extra signals. And it can apply to other types of communication. So handshake protocol is very simple to implement. You just saw that with the coding and the hardware. And in the next unit, unit 5, I'm going to deal with a more common type of interface, which is the serial interface. And you'll see the Arduino supports two of them, the USB serial communication, and one called I2C, which is very common in automotive, aerospace, really many different areas, and computers, phones, inside your phone, you have serial communication, and devices will talk to the processor on your phone using I2C. So anyway, that's in Unit 5.